Okay, so now we're going to put it all together. So by putting it all together for part three, it means just your prior knowledge, anything that can help us build, make connections. So talking about transformations, talking about the exponential function, talking about the rules that you wrote down from your do now today. That's what we mean by putting it all together. So these are going to be page 89 of your notes. I'd like y'all to acknowledge that I actually printed them correctly. Just want to let y'all know your booklet is a booklet today. Felt like that was a big accomplishment. So here we go. So starting off, we're going to talk about, let me hide this thing right here. We're going to be talking about whether it's a growth or a decay. Okay. On our notes on Tuesday, part one, we talked about if it's a growth, then your base. So in this case, a growth means your B is greater than one, right? You all remember us talking about that? Okay. If it's a decay, that means that your B is less than one, but greater than zero. Okay. So we're going to discuss how to determine whether we have a growth or decay just from a given function model. Okay. So up first, we have f of x equals e to the 5x. What we're going to use here is our power property and to separate. So we're going to use the power property, but we're undoing the power property. The power property said that if you have x a to the b, it becomes x times a to the b, correct? So we're going to use this property to undo this, to separate our variable from our coefficient. Cool? So this is going to become f of x equals e to the fifth, and then our x is on the outside. That's what makes that possible, is the power property that you wrote down on page 90. Okay, so from there, we're now going to just focus on the base. And we're going to ask ourselves, is e to the 5 bigger or smaller? So we have e to the 5. Is it greater than 1 or less than 1? It is going to be greater than 1 because e to the 5 is greater than 1. That means that this is a growth. Because remember, we said e is approximately 2.72, right? And if I do 2.72 times 2.72 times 2.72 times 2.72, I don't know how many times I'll say it, but you get the gist of it. It's going to be greater than 1, right? All right. How do we feel about so far using the power product? Easy enough? All right, let's try it again. So we're using the power property for example B, and we have e to the negative x over 2, okay? So when we use the power property, we are again, we're keeping the e, but we're separating the x. So when we take out x, what we're left with is what? If I have a variable there and there's no number, who's there? What number's there? 1. Casper the friendly 1. So if I take out the x, then Casper has to pop up. No variable is actually ever by itself. Casper the friendly 1 is always there. Okay, so now we have e to the negative 1, negative 1/2 times x to the x power. So this time our base is e to the negative 1/2. Based on our negative property, our negative power property, this has been a bad power. What did we say a bad power belongs? In the basement. I know that's terrible, but you get it. You get where I'm going with it, okay? So, is our base greater than 1 or less than 1? It is less than 1. Make sense? And because it's less than 1, then this is a decay model. If we look back on our part 1 notes, our decay model, our growth model means that it's increasing from left to right. And our decay model means that it is decreasing from left to right. Yes? All right. How do we feel about using our exponent properties to determine if it's a growth or decay? Doable? Okay. Example 3. Now we're going to talk about translations and dilations. So for this property, we're going to be using our product and quotient properties. Okay, so we're using our product and quotient properties of exponents. So your product property, which you wrote down already on page 90, you wrote down that if you have two variables, two exponents with the same base, when you combine them, you're adding their powers, correct? So we want to undo this. So these two have already been added, which means that I can rewrite it as a multiplication. Does that make sense? So this becomes f of x equals e to the x plus e to the third. It's not plus. Y'all were just going to let me do that to myself. You saw nothing. Times. There you go. Times e to the third. So now what this becomes are two separations. So e to the third is now my a. It's now my factor that's outside being multiplied. So this can be written as e to the third times e to the x. So this is my a. E to the third is a greater than 1 or less than 1? Greater than 1. So this is a vertical stretch. I can spell by a factor of e to the third. And that's because A describes whether it's a vertical stretch, compression, or reflection, right? And because it's greater than 1, that makes, since the absolute value of it is greater than 1, that makes it a vertical stretch. Okay, let's try the next one. So the next one here, we have, it's a highlighter. We have e to the x minus 5. So e to the x minus 5, this time we're using our quotient property. And you wrote this down on page 90, which in theory should be right next to it, right? If you did it in the notebook. So quotient property is saying that if you have two numbers that have the same base, to simplify this, you subtract their powers, right? Okay, well, we're going to undo that. So if I have e to the x minus 5, I'm now going to separate it into a division problem. So it becomes f of x equals e to the x divided by e to the 5. Because based on the quotient property, I can go back and forth. What this means now is that my a is 1 over e to the 5 times e to the x. The goal is to get your e, your base, and its variable by itself. Because e is not a variable. E is a number. It's an irrational number, but it is a number. Okay, so now it's by itself. So this is our a. And is our a greater than 1 or less than 1? It's less than. So this time, instead of a vertical stretch, we have a vertical compression. By a factor of 1 over e to the 5. If I have a hole and no matter what the number is on the bottom, if I just keep cutting it, it's going to be less than 1. Does that make sense? Okay. Do you see the difference between using the product property and using the quotient property? Cool. Okay. So with this, what kind of assumption can we make? Based on what we have here, we can almost assume that product properties are going to be what? What type of translation? It's going to be what? It's going to be, well, the growth or decay, it's going to depend on whether it's negative or positive, right? So the growth or decay is going to depend on if it's negative or positive. For an A value, it's because it's going to cause it to reflect, right? I'm going to go shoo, shoo, shoo. But with the product, what that's going to help us know is that if it's a stretch or a compression, right? So if I am using product property, it appears that it's going to be more than likely a vertical stretch. Does that make sense? If I'm using quotient property, it appears that it's going to be more of a vertical compression, right? Because the one is being multiplied and one is being divided, right? I'm compressing, I'm cutting it down if I'm dividing it. All right, so keep going on with all the magic of exponential functions. Can be expressed using other bases, meaning the value stays the same even if the function changes, okay? So here we have f of x, excuse me, we have f of x equals 3 to the x, and we want to express it in terms of e, okay? I'm supposed to, according to College Board, give you a time to process and think. How do you think I can take f of x equals 3 to the x? So based on unit 2b, and then understanding exponent properties, how do you think you can take this and turn it into an e? Okay, so I'm going to let you ponder on that for a moment, and then we'll guide through it together. So take time, think how can I make that happen? And it says that I can take any and turn it into it. So, all right, let's talk about it. So, our goal is to take this and make it into a base of e. So, to do that, we're going to set it equal to it. I want you and this to be the same. I want them to have equal values. So, if I want them to have equal values, what can I do to make it happen? Well, I got to worry about their variables, right? I have to work on getting the variables and transforming that. So, we're going to use what we said is the inverse operation. So what is the inverse operation of E? Hit part 2 of our notes. What was that? Inverse operation of E. Part 2 notes that we just did. Natural log. Thank you, thank you. So natural log. So we're going to take the natural log of both sides. What I do to one side, I do to the other. So what ends up happening is, what do we say once natural log and E are with each other? They become what? They cancel each other out, right? They're inverse operations. So they cancel each other out. So this is going to go away. So our E now goes away. So we're left with the natural log of 3 to the x equals k times x. Okay, now we're here. So in unit 2b, we talked about our power to coefficient rule, right? So that means that this x can now become a coefficient, right? Do y'all remember us doing that? The power to coefficient in unit 2b. So we have x natural log of 3 equals k times x. Okay, if I have a variable on the left and the right, what is that? What happens to it? It cancels out. So bam, canceled out. And what we're left with is our k value. So our k value that we're left with is, bad choice of color. No matter how much I love purple, it does not act like a good highlight. Let's just use regular yellow. Boring, but there you go. Okay, so now we know the value of our k. So our k is natural log of x. So what that means is that when I want to write an equivalent form, so you see nothing. Erase, erase. So that means it is equivalent form 3 to the x equals e to the natural log of 3 times x. That would be its equivalent form. That would be what would make it true. So what we're going to do is we're going to use Desmos to prove this to be true. So if you have your computer, I would like for you to go to Desmos graphing, and you're going to graph 3 to the x, and then you're going to graph e, natural log of 3 to the x. I need my mouse because, ClickPad is terrible. No, my friend. There we go. we're going to go to our Desmos. And once you're here, you're now going to type in our left side, which is 3 to the x. So left side, f of x equals 3. Remember, shift 6 to get your power. Okay, and our right side, we're going to call it g of x. How about that? Equals, and we ended up with e shift 6. Now, Desmos a little finicky. Sometimes it'll let you write the whole thing without parentheses. So we're going to test it out and see if it lets us be great or not. Natural log of 3 times, oh, see, told you, finicky. We're going to go ahead and put in parentheses, natural log of 3 times x. Oh my gosh, what do you notice? What do you see happen? Anyone? Everyone? They overlap. So that's proof that they're what? They're the same. So now we've proved visually that what we got mathematically, they're the same, right? They're equivalent functions. How do we feel? Okay, so I do like this feature. Y'all know I'm true in pride to Sylvie and her grandkids, but Sylvie has limitations. So we will give Desmos this. I like the fact that I can unhide and reveal. So you can see how we had our original one, f of x, and then when we graphed our g of x, it overlapped, and therefore they are equivalent functions. Okay, so that's what it means when you can take any exponential and write it as a exponential with base of e. Okay, and you can always check yourself, beauty of math. Okay, you can always check yourself, and if it don't overlap, then that means you may have did something wrong. Okay, so guess whose turn it is? If you said you're correct. Okay. All right, your turn. So this time you have f of x equals 0.2x, and you're going to convert it to a base of e. So looking at what we did. Okay. Remember, you guys can talk to each other. I know we discussed mornings are not exhausting. I'm really good at things I make it, and that's usually after 9 o'clock. Good job. You solved pattern. You call it pattern. And not doing that, once you see the pattern, it eliminates all the words. All right, and remember, if you're not sure if you got it right, that's what Desmos allows you to do, right? Check yourself where you graph the left or right, and if they overlap, then you're a genius. All right, so we're looking pretty good. I'm gonna let Austin, because Austin, I walked around and he just wrote the answer. He didn't show any work, and he just went straight to the answer. So, Austin, what led you to that conclusion?
I'm explaining what I noticed on the last one. I was just kind of formula with 3x plugged in, but plugged in 0.2x instead.
There we go. So Austin noticed that the base of the argument of your natural log is the base of the exponent. And so instead of him going through the process, he made this conclusion from seeing, oh, it's just the argument is the base of the exponent. So he went straight to the fact, well, what is the base of my exponent? 0.2. So therefore, it's going to be the argument of the natural log. Do y'all see it now once he stated? Okay, I love that all of you did the work and showed the steps for it. So good job on that. Don't be mad. That's what I wanted you to do. But the conclusion here is the base of the exponent, if you're writing it as a natural log, as an E, it's going to be the argument of the natural log. Does that make sense? Let me protect it so I can write it correctly. Okay, yeah? So that's our conclusion. Perfect. Now, why is all this important? Where does it come to? Our dreaded word problems. Dun, 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 dun. So what we're going to do is we have our word problem up here. I would like for you to read it first, and then I would like for you to go through and highlight important numerical information and to circle our question, okay? What are we trying to solve? So you're highlighting important information, and then you're circling the question. What is it wanting us to solve? Or statement of solution. And her name is Rohisa. They matter. Or you can call her Ro for short, you know, whatever makes your heart happy. We're going to mark our text first, and then we'll proceed. So we've been building up exponential knowledge to solve a real world problem for Rohisa. Not a problem. I'm not cool to worry about, but. So when we talk about our rate and how we turn our rate and the rate, sorry. So how is that function? What do you want to go ahead and start? See that we're almost all done marking our text. Good job. Don't keep too early. You gotta get your activity. Oh. All right. Okay, so from marking the text, we should have highlighted some important stuff, right? So what's important here is our homegirl. She has 20,000 gallons, right? That's what it holds. Okay. She noticed that the pool seems to be losing water. So I'm losing water at a continuous rate. So at a rate of 1% every hour, she's losing water. And it wants us to write. So we're going to write an exponential model. That's what it's asking us to do. Write an exponential model in the form of a times b to the x. Correct? So that means we need to know two things, a and b. Okay. Your a, when we talked about the graph of an exponential function, your a is always your initial. Okay. So your a is where are you starting? What is your initial? So for this problem, what is our a? 20,000. So we know a equals 20,000. Your b is your growth or decay factor. And in this problem, if she's losing, what do we have? It's a decay. Because it's a decay, that means we know it has to be less than 1, right? So she's losing. Normally, we would be at 100%, but she's losing how much each time? 1%. Does that make sense? So our B equals 100% minus 1%, which is 99%. And 99% as a decimal is 0.99. Do I now have an A? Do I now have a B? So can I write her function? Yay, nay. Yay. So we have f of x equals, what's our a? 20,000 times our b, and our b is 0.99 to the x. So this would be her function model. Because she's continuously losing the water, right? Now, is it a fast leak? No, it's pretty slow. But eventually she's going to run out of water. Okay. The beauty of this is that if I wanted to actually calculate when she's going to run out of the water, I'm going to come over to here and I'm going to type in 20,000.99 shift 6 to the x. I don't see it, so I'm going to have to like do a little zooming out. But can you see that we were correct about it being a decay model? Yeah. And it's getting closer and closer and closer. But at the rate that it's going, as you can see, it's going to take a pretty long time for it to be completely out, right? So she can solve her problem before this pool runs out of water. I can open the table and I can see that she still has a lot of water after 2 hours. Now I can type in 2,000. Okay, she's out of water at this point. It's a little high. Let's try 1,000. Okay, after 1,000 hours, she has 0.86 gallons of water, right? Again, I'm not a big fan of decimals all the time, but this is a pretty cool feature that you can just pop it, put in, and see how it grows. Cool? It didn't ask us for that. It just asked us for what? The function. Did we make the function? Well, yes, we did, because we're geniuses. All right. Let's talk about another real example of where exponential modeling comes in handy. So in 2017, the average value of a vintage Bronco SUV in perfect condition was 47,025 compared to 23,400 5 years earlier. Write an exponential function to model this scenario, assuming the percent increase in value of the vintage Bronco occurs continuously. Then use your model to estimate the value of the vintage Bronco. Okay. So first we're going to create, we're going to mark our text and we're going to then create a table from what we got. So we have in 2017, it was worth 47,025. 5 years later, it was worth 23,400. So what is this price of this SUV doing? Huh? Increasing? It's increasing, right? 5 years earlier. Did y'all say increasing or decreasing? Oh, I was like, what? Increasing. Yes. It's getting better, right? For whatever reason, people want this Bronco. I don't know why, but the value of the Bronco is increasing, right? So when we make our table, we're going to look at those values. I need my pen back. Pointer. Okay, so it wants us to use this. We're going to create a model. So it wants us to create a model to estimate the value in year 2021. So we're going to make a table of what we have. So we have our years and we have our cost. So in 2017, it was worth $47,025. 5 years earlier, so 5 years earlier to 2017 is 2012. So in 2012, it was only worth 23,400. This Bronco must have been in a movie or something, like I don't know what else would make it increase that much, but and he wants to write an exponential model. So we could do this by hand. However, we're going to let Desmos be our friend. And we're looking for our exponential model. So using Desmos, we're going to use our regression model. So we have y1 tilde a times b x1. That's what we're putting in. Y'all remember putting regression models into Desmos? Okay. We're going to make sure that when we do this, we have to check the log box. Okay. So we want to make sure we check our log mode when we do it. The reason why I like using Desmos is because you can still use your 2017. Sometimes with exponentials and the handheld, you have to have smaller values. So you would normally start off with maybe 0 and -5 or um, 0 and 5, but we don't have to in this case. Does that make sense? All right. So here we're going to create our table. In our table, we have 2017. And what was the value again? That's 47. 47 what? 25. And then in 2012, what's my value? 23, 400. Okay. So now I've made my table, and now we're going to write our regression model. So we have y1 tilde a times b shift 6 x1. If it had the log box, we would make sure it's checked. Now, it gives us a very, 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 very large a value, which again is an example of why we may want to reduce our what values? Our years, right? So instead of having 2012 and 2017, we're going to make this 0 and we're going to make this 5 because that's the separation. Okay. So it's still a 5-year separation. We're just changing it so that we end up with what kind of numbers? Friendlier numbers. Do we see that? And it auto updates your regression model and everything. So you don't have to change anything. You don't have to do anything. I'm going to hit the auto fit button, the magnifying, so I can see it. And so here's my regression model. The car value went from here to here, and the car value is going to keep doing what? Increasing, right? So now I'm going to write the function model. So writing the function model, we have f of x equals 23,400 times 1.1498 shift. So that's our regression model. And it asks us for what year? Mm-hmm. So we have to change the years to 0 and
My graph doesn't look like that.
so go right here. No, auto. Oh, yep. All right. The reason why we write it as a function is so that we can plug in whatever we need. Now that we have it a function, it asks us for 2021, right? 2021 is how many years after 2012? 9, right? Even if you didn't want to do the math, the beauty of this is you can write that in there. If I have f of 2021, how many years after 2012 is that? 9. And it'll do it itself. And it'll tell you, based on your growth, this is the new value of your vehicle. So the projected value would be $82,129.55. Okay. So let's recap what we did here. We tried with just the years, right? And the years were too what? Too big, right? So we adjusted our x values, and the distance is still the same, 5-year gap. This is our initial. This is our 5 years later. It gave us our model. We wrote our model as a function. And from that function, we were able to answer the question. The question said, in 2021, what is the value of the Bronco, right? So the value of our Bronco would end up being 2021 minus 2012, which is a 9-year gap. And it comes out to be $82,189.55. And that is how you would use Desmos to solve your exponential model. How do you feel? Good. Because guess what? You're about to each get an exponential model to work at your table. Yay. You had to know it's coming.